SwayamPrabha. Digital India. Educated India.
Welcome to the third lecture. In the previous lecture, we looked into the equivalent elastic modulus along direction 1, 2 and also the shear modulus in 1, 2 plane of a composite ply in terms of the same properties of the constituents. We will continue from there today. Now, we will look into the Poisson's ratio. So, we have two Poisson's ratio, one 2 which we call minus E2 by E1. So, Poisson's ratio, as we know that when it stretches at one side it compresses at the other side or vice versa. Now, the direction of those two perpendicular stress with a negative sign is a Poisson's ratio. Now, nu1 2 is minus E2 minus epsilon 2 by epsilon 1 which we call major Poisson's ratio, and nu 2 1 is minus epsilon 1 by epsilon 2 which we call minor Poisson's ratio. Now, again if we draw the idealized diagram, we have V at fiber at one side, M at other side, and let us say it is loaded in direction 1. So, when it deforms, it would deform in this way. So, it will expand in one direction, contract in other direction. Now, the deformation along the contraction along the fiber, let us call it delta f, and contraction along direction 2 of the matrix part, let us call it delta m. And then we have this as our axis 1 and this as our axis 2. And again we can write delta is equal to delta m plus delta f, and delta m is equal to the epsilon 2 multiplied by epsilon 2 of the matrix multiplied by Bm. So, let us write this dimension as Bm and this as Bf, and this is epsilon 2 f of the fiber multiplied by Bf, and then here we have epsilon 2 multiplied by Bm plus Bf. Now, this can be written, these strains can be written in terms of the strains in the longitudinal direction. So, epsilon 2 is nothing but minus nu 1 2 multiplied by epsilon 1 to Bm, and this is minus nu 1 2. So, this for the matrix, and for matrix actually we can write nu 1 2 m is just nu m, and nu 1 2 f multiplied by m multiplied by Bf, and here it is an equivalent quantity. So, equivalent nu 1 2 of the composite multiplied by epsilon multiplied by Bm plus Bf. Then again we have epsilon 1, same here. We saw that when it is loaded in the longitudinal direction, the strain along the longitudinal direction are same for matrix and fiber, and that is epsilon 1. So, if we cancel epsilon 1 and bring Bm plus Bf in the denominator at the right hand side, we can write nu 1 2 is equal to nu m multiplied by Vm plus nu 1 2 f multiplied by Vf. And again if we look at the variation of this quantity nu 1 2 with Vf, it gives a linear variation as the equation says. So, when Vf equal to 0, it is just nu m, and when Vf is equal to 1, it is nu 1 to f. So, this is Vf equal to 1 here, and we have two nu 1 2s for composites. So, nu 1 2 divided by E 1, that is equal to nu 2 1 divided by E 2. So, E 1 and E 2 are different. So, nu 2 1 and nu 1 2 are also different, and they follow this relation. So, if I know one of the Poisson's ratio and if I know the elastic modulus along direction 1 and direction 2, we can find out the other Poisson's ratio as well. Now, we will talk about the stress strain relation, and we will go towards the stress strain relation in a thin ply. For that we need to define some quantities. We need to define orthotropic material. We need to define the elastic stress strain relation for orthotropic material, and then from there we will in a 3D, and then from there we will look into the stress strain relation in a ply in 2D. Now, orthotropic material is material with three mutually perpendicular planes of symmetry. So, it has unique properties, unique and independent also. We can just say unique. Unique properties in three mutually perpendicular directions. Three and then there is something called spatially orthotropic, where reference system, which means the axis system, reference system coincides with principal material direction. So, x y z coincides with 1 2 3. and we will see that when it is specially orthotropic, some of the couplings does not exist. We will see that later on. Now, for a orthotropic material, the stress strain law is this. It is symmetric. So, we can populate this side. So, stress is equal to C matrix multiplied by strain, and C matrix is this. This is for a orthotropic material. And then comes another material which is transversely isotropic. So, it has one plane of isotropy, which means properties are same in one direction or in one plane. So, for example, in case of piezoelectric sheets, we saw that the properties are same in the in plane direction, but in the out of plane direction properties are different. In this case, the C matrix becomes C11, C12, C23, and then we have C22, C23, C22, and this is symmetric. So, in this case 2-3 plane is the plane of isotropy. So, that is why we can see that C22 and C23 are same, and similarly shear modulus here and here are also same. And isotropic materials are same material property in all three directions. In this case, the C matrix turns out to be C11, C12, C12, 0, 0, 0, and then we have C11, C12, 0, 0, 0, C11, zero 0, here we have 0, C11, C12 by 2, and where we have C11 minus C12 by 2. This 0 we do not need to write because it is symmetric. And this is symmetric. So, this is our isotropic material. Now, we are in a position to find out the constitutive relations in a thin ply. So, we have seen that the stress is equal to the C matrix multiplied by the strain matrix for a orthotropic material, and our materials are orthotropic. So, C12, C13, 0, 0, 0, and then we have C21, C22, C23, it is symmetric. So, C12 and C23 are same, C31, C32, C33, 0, 0, 0, 0, 0, 0, we have C44, 0, 0, 0, 0, 0, 0, C550, and we have 0, 0, 0, 0, C66, and this is multiplied with epsilon 1, 2, epsilon 3, epsilon 4, epsilon 5, epsilon 6, and here we have stress. Now, in this case we assume that there is a plane stress condition that exists. So, we have plane stress condition because it is thin ply, because the plies are thin. So, when it is plane stress condition, we can say that sigma 4 is equal to sigma 5 is equal to sigma 3, they are all 0. So, any stress in the direction 3 is 0. So, we have sigma 1, sigma 2, then 0, 0, 0, and sigma 6, and sigma 6 as we know it is nothing but tau 1 2. So, if we solve this, if we follow this equation, what we get here is sigma 1 is equal to C11 multiplied by epsilon 1 plus C12 multiplied by epsilon 3 plus C1 plus C13 multiplied by epsilon 3, yes, and then we have sigma 2 is equal to C21 multiplied by epsilon 1 plus C22 multiplied by epsilon 2 plus C23 multiplied by epsilon 3, and here we can see that there are a lot of zeros, and that gives me that 0 is equal to C31 into epsilon 1 plus C32 into epsilon 2 plus C33 into epsilon 3, and from here we get epsilon 4 equal to 0, epsilon 5 equal to 0, and finally we have sigma 6 is equal to C66 into epsilon 6. Now, we will keep this equation. This is finally going to help us derive the stress strain relation for a thin ply. Now, before that we have to know what these C's are. Now, if you want to know the C, first we would write the relation in the inverted form. So, epsilon 1, epsilon 2, epsilon 3, epsilon 4, epsilon 5, epsilon 6 is equal to a S matrix multiplied by sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6, where S matrix is written as one by E1 minus nu 21 by E1 minus nu 31 by E1. Then we have nu 12 by E2 E1 So, we have minus nu 2 1 by E 2 and we have minus nu 3 1 by E 3, and here we have minus nu 1 2 by E 1, here we have 1 by E 2 and here we have nu 3 2 by E 3, and then here we have nu 1 3 by E 3 minus nu 2 3 by, so this is E 1, E 1 E 2 and here we have 1 by E 3. So, 0 0 0 we have 0 0 0 0 0 0 and then 0 0 0, here we have 1 by G 1 2 0 0 0 0 0 0 1 by, so this is G 2 3 and here we have 1 by G 3 1 0 and here we have 0 0 0 0 0 1 by G 1 2. Now, that is our S matrix. So, if we compare the relation that we had before, there we had sigma is equal to C multiplied by epsilon. So, that gives me that C is just inverted form of S matrix. So, with that we can know C in terms of these material properties E 1 E 2 E 3 G 1 2 G 2 3 G 3 G 3 1 and nu 1 2 nu 2 3 and nu 3 1. So, then if we combine everything, so we know the C matrix in terms of those E's, nu's and G's, and then we have this relation. So, using these relations and this C matrix in the form of those E's, finally we get so we can say that satisfying the plane stress condition, we can write this as Q 1 1 Q 1 2 0 Q 1 2 Q 2 2 0 and we have 0 0 Q 6 6, which is equal to epsilon 0 epsilon 2 epsilon 6 and epsilon 2 we can write gamma 1 2 also, this we can write tau 1 2 also. Now, so these Q's come in terms of the C's and we know the C's in terms of the E's, nu's and G's. So, finally, that expression looks like the expression for the individual components of that Q matrix looks like this: Q 1 1 is equal to C 1 3 minus 3 1 3 square divided by C 3 3. So, we have E 1 divided by y 1 minus nu 1 2 nu 2 1. Q 1 2 is C 1 2 minus C 1 2 C 2 3 divided by C 3 3 and that comes as nu 1 2 E 2 by 1 minus nu 1 2 1 minus nu 2 1, or we can write nu 2 1 E 1 by 1 minus nu 1 2 1 minus nu 2 1, and then we have C 2 2 is Q 2 2 is equal to C 2 2 minus C 2 2 square by C 2 2, which looks like E 2 by 1 minus nu 1 2 by 1 minus nu 1 2 nu 2 1, and then we have Q 6 6 which is just C 6 and which is just equal to G 1 2. Now, this is called this generally is called stiffness matrix Q, and this can be written in the inverted form as this also, epsilon 1, epsilon 1, epsilon 1, epsilon 2, epsilon 6 as S11, S120, S12, S220, 00, S66, and here we have sigma 1, sigma 2, sigma 6. S11 is 1 by E1, S12 is minus nu 12 by E1, which can also be written as minus nu 2 1 by E2. S22 is 1 by E2 and S66 is 1 by G12. So, Q is often called stiffness matrix, but do not confuse it with stiffness term, which we define as load by displacement, and this is often called compliance matrix. So, now we have defined the stress strain relation in a thin ply in the principal material system. Now, later on we have to convert it to a global XY system. So, that we will do in the next lecture. So, let us end this lecture here. Thank you.